In this video, what I'd like to do is to go over another problem of 2D static equilibrium. And in this problem, what do we have? We have this block, this 40 kilogram block that is held in static equilibrium by this string at CB and a spring that is stretched at BD. What we are asked to do is we are asked to figure out the unstretched length of the spring and the force in CB. So what this means is this spring originally had some length like this, and then we pulled it till it got to point B, and at point B it's able to hold this system in equilibrium. And we want to figure out what that original unstretched length is. How do we go about this? First thing, we need to draw a free body diagram. And point B seems like a good candidate to start with the free body diagram because this spring and the string are connected to point B. So let's look at point B. Well, at point B, we have this spring right here. This string is in tension. Strings can only support tension. So we know we're going to need to draw a force that goes away from the point we're looking at, which is B. And right now, let's call this the tension of BC. So this will be a force we're interested in looking at and figuring out what it is, but we don't know it yet. Another force that we're looking at is this spring force. So like I had said before, this spring is pulled in this direction. So we're pulling it with that force. That means the force we need to put it in our free body diagram is the force with the spring that wants to get it back to its original position. So we pull it towards B, the spring wants to pull away from B. So our spring force is going to go in this direction. And right now, let's just call it the force of our spring. And finally, we have this rope right here. And right now, we're going to call this a rope. I'm going to show the trick you can use to make this analysis a little faster. But right now, we only know that this is a rope. So we're going to have this, the ropes can only support tension. So a tension force that goes away from point B. And it's just going to be this tension of, we'll call it BA. Well, now this isn't good right now, right? We don't know what TBC is. We don't know what TBA is. We don't know what FS is. Well, we do know we have another equation for FS. Maybe that will help us. We know that this is equal to K times delta S, the spring coefficient times how far it was stretched. But we weren't given delta S, so we would still have 3 unknowns with 2 equations. So what do we do? Well, what we could do is you could have initially seen that this TBA right here is just equal to the weight of whatever this block is, and this would have been equal to my mass, 40 times 9.81. This will give, this is in kilograms. This is in meters per second squared. So that will give me a force in newtons. And then everyone's happy. And what is that number? 40 times 9.81, 392.4. But what if you didn't see this? How could we, if you see it, it's good. If you didn't see it, what you would have needed to do, you would have needed to say, okay, well, I need to find an alternate way to figure out what one of these pieces of information are. If I go back and I look at my diagram, the only place I could go to is what's happening with this block right here. So now I would need to perform 2D static equilibrium on that block. So if I perform 2D static equilibrium on that block, first I draw a free body diagram of that block. On this block, I have a weight that goes down, right? It's that 40 times 9.81. So this is equal to 392.4 newtons. And I have this string that goes up. So my string, and I know that it's going to be that same, I'm going to just call it TBA. I know that it's the same string. So this will be TBA. And then I need to go to step 2 of my procedure. And step 2 of my procedure says, okay, I need to use my equations of motion, equations of equilibrium. And I only have forces in the y direction. So I'm going to call up positive. So I have TBA minus 392.4 is equal to 0. And I get TBA is equal to 392.4 newtons. This is exactly what we had right here. So all we're doing in our head is we're saying, okay, we have this mass that has a weight and a rope, but that's the only force that acts on this rope right here. So that means all of the weight that goes down needs to be into this, needs to be transferred into this cable right here. So it's just a shortcut if you're able to see it. It saves you a little bit of time. If you're not able to see it, you'd have to go through starting over here, then going and doing this free body diagram, doing this equation of equilibrium. Again, it's fine. You'll get the right answer. But you can save yourself a little bit of time whenever you see a string that only has, one force that's going to be acting on it. So when anything is suspended by one string like this, you can sort of use this shortcut and know that that weight has to be the force on that string, which is what we have right here. Okay. So now we want to do step 2. We want to apply, for this main free body diagram at B, we want to apply my equations of equilibrium. In this one, I'm going to need to use my x and my y. So let's start with the sum of the forces in the x is equal to 0. I'll say anything to the right is positive. So let's look at this. Well, TBC right here, TBC is pointing, if I decompose that into x and y, I have something that goes this way and something that goes this way. So it's pointing, my x component is pointing to the left. I said to the right is positive. What does that mean? That means that my x component is going to be a minus TBC. And, well, I need to figure out what this component is. It's a 45-degree angle. So I'm looking for this side of that triangle right here. That's going to be the cosine. So it's going to be minus TBC times the cosine of 45. Great. So now let's look at f of s. I could use k delta s, or I could use f of s. It doesn't matter. I'll need to do all the steps eventually. So just for writing it, I'm just going to use f of s. But if I decompose this, okay, that x component is pointing to the right. That's in the same direction as my positive, that of what I called positive. So I'm going to add in plus f of s, and I need to figure out what this component is. What is my x component? Well, my x component is actually, we need to figure out what theta is. And I can figure that out from the problem that was given to me. I know that here's a little triangle I can construct. I know that this height right here is 2 meters. I know that this length right here is 3 meters. So that means I can figure out what this angle theta is, right? I know that angle theta from a right triangle. I'm going to have my opposite side, my adjacent side. Go look at SOHCAHTOA and verify it. But that means theta is going to be the inverse tangent of 2 divided by 3. And that means theta is going to be 33.7 degrees. So if I want that x component, again, verify this with SOHCAHTOA, but I'm going to need to take the cosine of 33.7 degrees. And then we're done with the x equation, right? There's nothing else. There's nothing else that has an x component on it. Now, we need to take the sum of the forces. Finish step 2. Sum of the forces in the y is equal to 0. We're going to call up positive. Now we got to look at all these forces. Well, again, if we decompose TBC, TBC is going in the upward direction. Upwards, what I called positive. So TBC is going to be added. We're going to have TBC. If this time we use, if for the x we use the cosine, for the y we're going to use the sine. So it's going to be times the sine of 45. And then what we're doing with the f of s, again, okay, this is also going up, right? If we decompose this, we can go sort of like this, up, or if you like going this way, it still goes up. So we're going up, and that's positive. So because it's positive, we're going to have f of s times the sine of 33.7. Now, we also at this point need to take care of this weight force. This weight force is pointing downward, directly downward. So down is the opposite of up. So it's pointing against our positive direction. So we're going to have to subtract out the 392.4 newtons. And then that's going to be equal to 0. So now we've done step 2. We have applied the equations of equilibrium to our free body diagram. The last step is to solve these equations for the unknowns and what we're looking for. Now, it doesn't matter what we're solving for. We need to figure out both of these unknowns. And actually, after we get that force in the S, we're actually not going to be done with that. But so it doesn't matter what you solve for. Just at first, verify you only have 2 unknowns, TBC and f of s, TBC and f of s. Okay, that's good. 2 equations, 2 unknowns. Let's go like this. We'll say f of s times the cosine of 33.7 is equal to 0. Is equal to, let's bring this to the other side of the equation. So we'll have TBC times the cosine of 45. I guess I'll solve for f of s. So I have f of s is equal to TBC times the cosine of 45 divided by the cosine of 33.7. I need to now put this into the second equation right here. So when I have TBC times the sine of 45 plus TBC times the cosine of 45 divided by the cosine of 33.7 times the sine of 33.7. And I'm going to bring this part of the equation over to, the other side of the equation, the 392.4. So that's equal to 392.4. Now, if you see this, this will be helpful. The sine of 33.7 divided by the cosine of 33.7 is the tangent of 33.7. So I'm going to just write that down. TBC times the sine of 45 plus TBC times the cosine of 45 times the tangent of 33.7 is equal to 392.4. Now we need to use the calculator. We need to figure out what the sine of 45 is in decimal and what the cosine of 45 times the tangent of 33.7 is using decimal. So let me clear the calculator. Let me just put these in first. and then I can write them in. So we're going to have 0.707 TBC plus 0.472 TBC is equal to 392.4. We're going to add those two numbers together, so plus 0.707. So we'll get 1.17 TBC. Which is equal to 392.4. So we get TBC is equal to 392.4 divided by 1.17, 300 and we'll call it 335. So this is equal to 335 newtons. So that's the force in this cable right here. Great, so that's part of what we needed to do. Then we can also figure out this F of S is equal to TBC times the cosine. Let me put a little squiggly line here. TBC times the cosine of 45 divided by the cosine of 33.7. But I don't really care about figuring out this forces, right? I don't care what the force is. I'm asked to figure out the unstretched length. So what I'm going to do is I'm going to make that substitution right now. I'm going to say K times delta S is equal to, I guess I could get that decimal number right now. So I can do the cosine of 45 divided by the cosine of 33.7, 0.85 equals 0.85 TBC. I know what TBC is. It's 335. So I know that the amount that I've stretched this spring is going to be 0.85 times 335 divided by K. K is right here. It's 180. So let's do that. 0.85 times 335 divided by 180. 1.58. 1.58 meters. All right, so this is saying the amount that the spring has stretched is 1.58 meters. Now, we just need to do one more step, right? This is this. If I look at this length right here, this is a length of unknown. This is my spring when it's stretched. I know that this length right here, when it's stretched, has a distance of 2. This has a distance of 3. And this is where the problem, it's a little tricky. I know that there's this unstretched length, and I'm going to just draw this in as a dotted line right here. This is my unstretched length. We'll call this L. I know that I have then stretched it an additional length, delta S. That's probably a good distance for it. So I know that this distance right here is 1.58 meters. Well, I can solve for what L is by looking at this. This is a right triangle, right? So I know this entire distance. Let's just call it S. S is going to be equal to the square root of 3 squared plus 2 squared, or what's that? 9 plus 4, the square root of 13, right? Pythagorean theorem. Let me just scroll down a little to give myself some room. So this entire distance is S. I know what my stretched length is, so I can figure out that distance L. I can say that S is equal to delta S plus L. S, the square root of 13, is equal to delta S, which was 1.58, plus L. Solve for L. My original length is going to be equal to the square root of 13 minus 1.58. It's not all under the square root. That would give me an incorrect answer. So my unstretched length L is equal to the square root of 13 minus 1.58. And I get this is 2.03. 2.03 meters. So this is also my answer. So those are the two answers I'm looking for. I have TBC is 335 newtons, and I have my unstretched length, which is equal to 2.03 meters. So hopefully this example has helped you with a 2D static equilibrium problem. If this video has helped you and you want to, please subscribe. It helps grow the channel. And please take a look at any of the other statics videos that you may like to look at in the playlist, and go and check them out. Thanks.